Okay, well, first of all, thank you so much for all the kind words. A lot has changed thanks to the incredible power of deep learning. I think my personal starting point, I was interested in artificial intelligence for a whole variety of reasons, starting from an intuitive understanding of appreciation of its impact. And also I had a lot of curiosity about what is consciousness, what is the human experience. And it felt like progress in artificial intelligence will help with that. The next step was, well, back then I was starting in 2002, 2003, and it seemed like learning is the thing that humans can do, that people can do, that computers can't do at all. In 2003, 2002, computers could not learn anything. And it wasn't even clear that it was possible in theory. Mm-hmm. And so I thought that making progress in learning, in artificial learning, in machine learning, that would lead to the greatest progress in AI. And then I started to look around for what was out there, and nothing seemed too promising. But to my great luck, Jeff Hinton was a professor at my university. Mm-hmm. And I was able to find him. And he was working on neural networks, and it immediately made sense. Because neural networks had the property that we are automatically programming parallel computers. Back then, the parallel computers were small. But the promise was, if you could somehow figure out how learning in neural networks work, then you can program small parallel computers from data. And it was also similar enough to the brain, and the brain works, mm-hmm. So it's like you had these several factors going for it. Now, it wasn't clear how to get it to work, but of all the things that existed, that seemed like it had by far the greatest long-term promise. Even though,
at the time that you first started working with deep learning and neural networks, what was the scale of the network? What was the scale of computing at that moment in time? What was it like?
An interesting thing to note is that the importance of scale wasn't realized back then. Mm-hmm. So people would just train, neural networks with like 50 neurons, 100 neurons, several hundred neurons. That would be like a big neural network. 1 million parameters would be considered very large. We would run our models on unoptimized CPU code because we were a bunch of researchers. We didn't know about BLAS. We used MATLAB. The MATLAB was optimized. And we'd just experiment, like what is even the right question to ask, So you try to gather, to just find interesting phenomena, interesting observation. You can do this small thing, and you can do that small thing. Jeff Hinton was really excited about training neural nets on small little digits, both for classification, and also he was very interested in generating them. So the beginnings of generative models were right there. But the question is like, okay, so you got all this cool stuff floating around. What really gets traction? And so it wasn't obvious that this was the right question back then, mm-hmm. But in hindsight, that turned out to be the right question.
Now the year AlexNet was 2012.
Yes.
2012. Now, you and Alex were working on AlexNet for some time before then. And at what point was it clear to you that you wanted to build a computer vision oriented neural network, that ImageNet was the right set of data to go for, and to somehow go for the computer vision contest?
Yeah. So I can talk about the context there. I think probably 2 years before that, it became clear to me that supervised learning is what's going to get us the traction. Mm-hmm. And I can explain precisely why. It wasn't just an intuition. It was, I would argue, an irrefutable argument, which went like this. If your neural network is deep and large, then it could be configured to solve a hard task. So that's the key word, deep and large. People weren't looking at large neural networks. People were, maybe studying a little bit of depth in neural networks, But most of the machine learning field wasn't even looking at neural networks at all.
Mm-hmm.
They were looking at all kinds of Bayesian models and kernel methods, which are theoretically elegant methods, which have the property that they actually can't represent a good solution no matter how you configure them. Whereas the large and deep neural network can represent a good solution to the problem. To find the good solution, you need a big data set, which requires it.
Mm-hmm.
And a lot of compute to actually do the work. We've also made advanced work, so we've worked on optimization for a little bit. It was clear that optimization is a bottleneck, and there was a breakthrough by another grad student in Jeff Hinton's lab called James Martins, and he came up with an optimization method which is different from the one we are using now, some second-order method. But the point about it is that it's proved that we can train those neural networks, because before we didn't even know we could train them. So if you can train them, you make it big, you find the data, and you will succeed. So then the next question is, well, what data? And an ImageNet data set. Back then, it seemed like this unbelievably difficult data set. But it was clear that if you were to train a large convolutional neural network on this data set, it must succeed if you just can have the compute.
And right at that time,
GPUs came
you
out.
and I, our history and our paths intersected, and somehow you had the observation that a GPU, and at that time this is our couple of generations into a CUDA GPU, and I think it was GTX 580 generation. You had the insight that the GPU could actually be useful for training your neural network models. What was that? How did that day start? Tell me. You and I, you never told me that moment. How did that day start?
Yeah. So, the GPUs appeared in our lab, in our Toronto lab, thanks to Jeff, and he said we should try these GPUs, and we started trying and experimenting with them, and it was a lot of fun, but it was unclear what to use them for exactly. Where are you going to get the real traction? But then, with the existence of the ImageNet dataset, and then it was also very clear that the convolutional neural network is such a great fit for the GPU. So it should be possible to make it go unbelievably fast, and therefore train something which would be completely unprecedented in terms of its size. And that's how it happened. And, very fortunately, Alex Krzyzewski, he really loved programming the GPU, and he was able to do it. He was able to code, to program really fast convolutional kernels, and then train the neural net on the ImageNet dataset, and that led to the result. But it was
it shocked the world. It shocked the world. It broke the record of computer vision by such a wide margin that it was a clear discontinuity.
Yeah. And I would say it's not just like, there is another bit of context there. It's not so much like when we say break the record, there is it's like, I think there's a different way to phrase it. It's that data set was so obviously hard and so obviously outside of reach of anything. People were making progress with some classical techniques, and they were actually doing something. But this thing was so much better on a data set which was so obviously hard. It's not just that it's just some competition. It was a competition which, back in the day,
it wasn't an average benchmark.
It was so obviously difficult, so obviously out of reach, and so obviously with the property that if you did a good job, that would be amazing.
Big bang of AI. Fast forward to now, you came out to the Valley. You started OpenAI with some friends. You're the chief scientist. Now, what was the first initial idea about what to work on at OpenAI? Because you guys worked on several things. Some of the trails of inventions and work you could see led up to the ChatGPT moment. But what were the initial inspiration? How would you approach intelligence from that moment and led to this?
Yeah. So obviously, when we started, it wasn't 100% clear how to proceed. And the field was also very different compared to the way it is right now. So right now we already used to, you have these amazing artifacts, these amazing neural nets who are doing incredible things, and everyone is so excited. But back in 2015, 2016, early 2016, when we were starting out, the whole thing seemed pretty crazy. There were so many fewer researchers, like 100, maybe there were between 100 and 1,000 times fewer people in the field compared to now.
Yeah,
like back then, you had like 100 people. Most of them were working in Google/DeepMind, and that was that.
Mm-hmm.
And then there were people picking up the skills, but it was very, very scarce, very rare still. And we had two big initial ideas at the start of OpenAI that had a lot of staying power, and they stayed with us to this day. And I'll describe them right now. The first big idea that we had, one which I was especially excited about very early on, is the idea of unsupervised learning through compression. Some context. Today, we take it for granted that unsupervised learning is this easy thing. You just pre-train on everything and it all does exactly as you'd expect. In 2016, unsupervised learning was an unsolved problem in machine learning that no one had any insight, any clue as to what to do.
That's right.
Jan LeCun would go around and give talks saying that you have this grand challenge on supervised learning. And I really believed that really good compression of the data will lead to unsupervised learning. Now, compression is not language that's commonly used to describe what is really being done until recently, when suddenly it became apparent to many people that those GPTs actually compress the training data. You may recall the Ted Chiang New York Times article, which also alluded to this. But there is a real mathematical sense in which training these autoregressive generative models compress the data. And intuitively, you can see why that should work. If you compress the data really well, you must extract all the hidden secrets which exist in it. Therefore, that is the key. So that was the first idea that we were really excited about. And that led to quite a few works in OpenAI, to the sentiment neuron, which I'll mention very briefly. This work might not be well known outside of the machine learning field, but it was very influential, especially in our thinking. This work, like the result there was that when you train a neural network, back then it was not a transformer, it was before the transformer.
Right.
Small recurrent neural network, LSTM, to those who remember.
The sequence work you've done, I mean, this is some of the work that you've done yourself, yeah.
So the same LSTM with a few twists, trained to predict the next token in Amazon reviews, next character. And we discovered that if you predict the next character well enough, there will be a neuron inside that LSTM that corresponds to its sentiment. So that was really cool because it showed some traction for unsupervised learning, and it validated the idea that really good next character prediction, next something prediction, compression, has the property that it discovers the secrets in the data. That's what we see with these GPT models, right? You train, and people say it's just statistical correlation. I mean, at this point, it should be so clear to anyone.
That observation also, for me, intuitively, opened up the whole world of where do I get the data for unsupervised learning? Because I do have a whole lot of data. If I could just make you predict the next character, and I know what the ground truth is, I know what the answer is, I could train a neural network model with that. So that observation and masking and other technology, other approaches, open my mind about where would the world get all the data that's unsupervised for unsupervised learning.
Well, I think so. I would phrase it a little differently. I would say that with unsupervised learning, the hard part has been less around where you get the data from, though that part is there as well, especially now. But it was more about, why should you do it in the first place? Right. Why should you bother? The hard part was to realize that training these neural nets to predict the next token is a worthwhile goal at all. That was
that
the
it
goal.
Would learn a representation, that it would be able to understand.
That's right. That it will be useful.
Grammar and
But but it just wasn't obvious.
Right.
So people weren't doing it. But the sentiment neuron work, and I want to call out Alec Radford as a person who really was responsible for many of the advances there. The sentiment, this was before GPT-1. It was the precursor to GPT-1, and it influenced our thinking a lot. Then the transformer came out, and we immediately went, oh my God, this is the thing. And we trained GPT-1.
Now, along the way, you've always believed that scaling will improve the performance of these models.
Yes.
Larger networks, deeper networks, more training data would scale that. There was a very important paper that OpenAI wrote about the scaling laws and the relationship between loss and the size of the model and the amount of data set, the size of the data set. When transformers came out, it gave us the opportunity to train very, very large models in very reasonable amount of time. But did the intuition about the scaling laws of the size of models and data, and your journey of GPT-1, 2, 3, which came first? Did you see the evidence of GPT-1 through 3 first, or was there the intuition about the scaling law first?
The intuition, so I would say that the way I'd phrase it is that I had a very strong belief that bigger is better. And that one of the goals that we had at OpenAI is to figure out how to use the scale correctly. There was a lot of belief in OpenAI about scale from the very beginning. The question is, what to use it for precisely? Because I'll mention, right now we're talking about the GPTs, but there's another very important line of work which I haven't mentioned, the second big idea. But I think now is a good time to make a detour, and that's reinforcement learning. That clearly seems important as well. What do you do with it? So the first really big project that was done inside OpenAI was our effort at solving a real-time strategy game. And for context, a real-time strategy game is like, it's a competitive sport.
Yeah, right.
Where you need to be smart, you need to have you need to have a quick reaction time, there's teamwork, and you're competing against another team. And it's pretty involved. And there is a whole competitive league for that game. The game is called Dota 2. And so we trained a reinforcement learning agent to play against itself, to produce, with the goal of reaching a level so that it could compete against the best players in the world. And that was a major undertaking as well. It was a very different line. It was reinforcement learning.
Yeah, I remember the day that you guys announced that work. And this is by the way, when I was asking earlier about there's a large body of work that have come out of OpenAI. Some of it seemed like detours, but in fact, as you're explaining now, they might have been detours. It's seemingly detours, but they really led up to some of the important work that we're now talking about, ChatGPT.
Yeah. I mean, there has been real convergence where the GPTs produce the foundation, and then the reinforcement learning from Dota morphed into reinforcement learning from human feedback.
That's right.
And that combination gave us ChatGPT.
You know, there's a misunderstanding that ChatGPT is in itself just one giant large language model. There's a system around it that's fairly complicated. Could you explain briefly for the audience the fine tuning of it, the reinforcement learning of it, the various surrounding systems that allows you to keep it on rails and let it give it knowledge and so on and so forth?
Yeah, I can. So the way to think about it is that when we train a large neural network to accurately predict the next word in lots of different texts from the internet, what we are doing is that we are learning a world model. It looks like we are learning this. It may look on the surface that we are just learning statistical correlations in text. But it turns out that to just learn the statistical correlations in text, to compress them really well, what the neural network learns is some representation of the process that produced the text. This text is actually a projection of the world. There is a world out there, and it has a projection on this text. And so what the neural network is learning is more and more aspects of the world, of people, of the human conditions, their hopes, dreams, and motivations, their interactions, and the situations that we are in. And the neural network learns a compressed, abstract, usable representation of that. This is what's being learned from accurately predicting the next word. And furthermore, the more accurate you are at predicting the next word, the higher the fidelity, the more resolution you get in this process. So that's what the pre-training stage does. But what this does not do is specify the desired behavior that we wish our neural network to exhibit. You see, a language model, what it really tries to do is to answer the following question. If I had some random piece of text on the internet which starts with some prefix, some prompt, what will it complete to? If you just randomly ended up on some text from the internet. But this is different from, well, I want to have an assistant which will be truthful, that will be helpful, that will follow certain rules and not violate them. That requires additional training. This is where the fine-tuning and the reinforcement learning from human teachers and other forms of AI assistance. It's not just reinforcement learning from human teachers. It's also reinforcement learning from human and AI collaboration. Our teachers are working together with an AI to teach our AI to behave. But here we are not teaching it new knowledge. This is not what's happening. We are teaching it. We are communicating with it. We are communicating to it what it is that we want it to be. And this process, this second stage, is also extremely important. The better we do the second stage, the more useful, the more reliable this neural network will be. So the second stage is extremely important too, in addition to the first stage of the learn everything. Learn as much as you can about the world from the projection of the world, which is text.
Now you could fine tune it. You could instruct it to perform certain things. Can you instruct it to not perform certain things so that you could give it guardrails about avoid these type of behavior? Give it some kind of a bounding box so that it doesn't wander out of that bounding box and perform things that are, unsafe or otherwise.
Yeah. So this second stage of training is indeed where we communicate to the neural network anything we want, which includes the bounding box. And the better we do this training, the higher the fidelity with which we communicate this bounding box. And so with constant research and innovation on improving this fidelity, we improve this fidelity, and so it becomes more and more reliable and precise in the way in which it follows the intended instructions.
ChatGPT came out just a few months ago. Fastest growing application in the history of humanity. Lots of interpretations about why, but some of the things that is clear. It is the easiest application that anyone has ever created for anyone to use. It performs tasks. It performs things. It does things that are beyond people's expectation. Anyone can use it. There are no instruction sets. There are no wrong ways to use it. You just use it. And if your instructions prompts are ambiguous, the conversation refines the ambiguity until your intents are understood by the application, by the AI. The impact, of course, clearly remarkable. Now, yesterday, this is the day after GPT-4, just a few months later. The performance of GPT-4 in many areas astounding. SAT scores, GRE scores, bar exams, the number of tests that it's able to perform at very capable levels, very capable human levels, astounding. What were the major differences between ChatGPT and GPT-4 that led to its improvements in these areas?
So, GPT-4 is a pretty substantial improvement on top of ChatGPT across very many dimensions. We trained GPT-4, I would say, between more than 6 months ago, maybe 8 months ago, I don't remember exactly. The first big difference between ChatGPT and GPT-4, and that perhaps is the most important difference, is that the base on top of GPT-4 is built predicts the next word with greater accuracy. This is really important because the better a neural network can predict the next word in text, the more it understands it. This claim is now perhaps accepted by many at this point, but it might still not be intuitive, or not completely intuitive as to why that is. So I'd like to take a small detour and to give an analogy that will hopefully clarify why more accurate prediction of the next word leads to more understanding, real understanding. Let's consider an example. Say you read a detective novel. It's like a complicated plot, a storyline, different characters, lots of events, mysteries like clues, it's unclear. Then, let's say that at the last page of the book, the detective has gathered all the clues, gathered all the people, and saying, okay, I'm going to reveal the identity of whoever committed the crime. And that person's name is...
Predict that word.
Predict that word,
Yeah,
exactly.
my goodness.
Right?
Yeah, right.
Now, there are many different words, but by predicting those words better and better and better, the understanding of the text keeps on increasing. GPT-4 predicts the next word better.
Ilya, people say that deep learning won't lead to reasoning. That deep learning won't lead to reasoning. But in order to predict that next word, figure out from all of the agents that were there and all of their, strengths or weaknesses or their intentions and the context, and to be able to predict that word, who was the murderer, that requires some amount of reasoning, a fair amount of reasoning. And so how is it that it's able to learn reasoning, and if it learned reasoning, one of the things that I was going to ask you is, of all the tests that were taken between ChatGPT and GPT-4, there were some tests that GPT-3 or ChatGPT was already very good at. There were some tests that GPT-3 or ChatGPT was not as good at, that GPT-4 was much better at. And there were some tests that neither are good at yet. I would love for it, and some of it has to do with reasoning, it seems. That, maybe in calculus that it wasn't able to break maybe the problem down into its reasonable steps and solve it. But yet in some areas it seems to demonstrate reasoning skills. And so is that an area that in predicting the next word you're learning reasoning? And what are the limitations now of GPT-4 that would enhance its ability to reason even further?
Reasoning isn't this super well-defined concept, but we can try to define it anyway, which is when you maybe when you go further, where you're able to somehow think about it a little bit and get a better answer because of your reasoning. And I'd say I'd say that our neural nets, maybe there is some kind of limitation which could be addressed by, for example, asking the neural network to think out loud. This has proven to be extremely effective for reasoning. But I think it also remains to be seen just how far the basic neural network will go. I think we have yet to fully tap out its potential. But yeah, I mean, there is definitely some sense where reasoning is still not quite at that level as some of the other capabilities of the neural network, though we would like the reasoning capabilities of the neural network to be higher. I think that it's fairly likely that business as usual will improve the reasoning capabilities of the neural network. I wouldn't necessarily confidently rule out this possibility.
Yeah, because one of the things that is really cool is you ask ChatGPT a question, but before it answers the question, tell me first of what you know, and then to answer the question. Usually when somebody answers a question, if you give me the foundational knowledge that you have or the foundational assumptions that you're making before you answer the question, that really improves my believability of the answer. You're also demonstrating some level of reason. Well, you're demonstrating reasoning. And so it seems to me that ChatGPT has this inherent capability embedded in it. Yeah.
To some degree.
Yeah.
One way to think about what's happening now is that these neural networks have a lot of these capabilities. They're just not quite very reliable. In fact, you could say that reliability is currently the single biggest obstacle for these neural networks being useful, truly useful. If sometimes it is still the case that these neural networks hallucinate a little bit, or maybe make some mistakes which are unexpected, which you wouldn't expect a person to make. It is this kind of unreliability that makes them substantially less useful. But I think that perhaps with a little bit more research, with the current ideas that we have, and perhaps a few more of the ambitious research plans, we'll be able to achieve higher reliability as well. And that will be truly useful. That will allow us to have very accurate guardrails, which are very precise.
That's right.
And it will make it ask for clarification where it's unsure, or maybe say that it doesn't know something when it doesn't know, and do so extremely reliably. So I'd say that these are some of the bottlenecks, really. So it's not about whether it exhibits some particular capability, but more how reliably.
To the degree
exactly.
Of it. Yeah.